All right, we can start. Okay. All right, hi everyone. Do we have a talk next Wednesday or no?
Not that I know of, unless
Okay, so next Wednesday there is no talk for improv. Yeah, if anyone wants to give an improv, like, we're happy to have you. And the next talk will be next Friday, or there's no talk on Friday.
Friday.
Okay.
Second.
Wow, okay, so after, good, okay, so next week we are taking a break, probably unless we have an improv. And so, okay, so for today, we're very happy to have one of our two very prominent Roberts tell us about streaming and communication complexity of load balancing. Oh.
Thank you. Yeah, thank you guys for coming. Yeah, today's talk will be on this paper with a joint work with Saper, Aaron, Zach, and Lapchi. Yeah, so I'll just get right into it. Oh, nope. Yeah, okay. All right, so the problem that we'll be studying is the load balancing problem on bipartite graphs. So we are given a graph, bipartite graph G, with vertex partitions L and R, where we will refer to L as the clients and R as the servers. And and our goal is to find a minimum load assignment of the servers to the client. So for each server, I want to assign it to one of the clients using one of the edges in the graph. And I want to minimize the maximum load. So the load on a particular server is just a number of clients that are assigned to it. So here you can see the max load is 3 because this vertex here has a three vertices matched to it. Yeah. Okay, so this is a problem. And then we also let n denote the number of clients on the left side. Okay. So this is a problem, and we will be studying it in the streaming and communication complexity settings. So in the streaming setting, we have that the edges arrive one at a time, and we can have potentially have one or multiple passes over the input. And in this setting, we are only allowed to use O tilde of n space, so typically much smaller than the size of the input. And the question is, what is the best approximation factor we can get on this load balancing problem given these constraints? Okay, so for some previous results, the best known upper bound for one-pass streaming algorithm was given by Conrad and Rosen in 2013, and it gives a O of root n approximation to this problem. And then the best lower bound we know though comes from just a 2 approximation, which is via reduction from maximum matching. So a big gap between the best and worst lower bound. Sorry, the best upper and lower bounds. Yeah. And then for multiple passes, we can do a bit better. Oh, sorry, we can do a lot better. In particular, with log n passes, we know how to get a O of log n approximation. And this was given by Conrad and Rosen. And this was recently improved by Saper and Aaron and Zach to constant factor approximation in log n passes. Again, the best lower bound that we know is only 2 approximation. So the question is, can we sort of improve the gap between the best upper and lower bound for this problem? So our main result, or our first main result in this paper, is that we show that we give a lower bound for the streaming complexity of this problem, which says that there is no semi-streaming algorithm, randomized or deterministic, which can attain an n to the 1/4 minus little o of 1 approximation to the load balancing problem. And this is for the one-pass algorithm. And this is for the one-pass setting. Yeah. So we can see that this n to the 1/4 greatly reduces the gap between the upper and lower bound. So okay, so now the way that we get this lower bound is by studying the problem in a similar one-way communication setting. So in this setting, our input graph, G, is given to us with the partitioning of the edges. So for example, here you can see that the edges are partitioned into these blue edges and these red edges. And then we have 2 players, Alice and Bob. Alice is going to get these red edges, and Bob is going to get these blue edges. And Alice is going to send a message to Bob of t bit of length t. And then Bob is going to receive this message and try to use it to compute a minimum load assignment. So in this case, Alice gets these edges and Bob gets these edges. So as long as Alice can give these two bottom edges over here to Bob, then Bob can compute the an output with maximum load at most 2. Yeah. So as you may know from before or not, a one-pass streaming algorithm immediately gives you a communication complexity protocol. In particular, if T is the space requirement of this streaming algorithm, then T is the O of T is the maximum length of the message that Alice has to send to Bob in this protocol. So this means that any lower bound on the communication complexity of this problem would also give you a lower bound on the one-pass streaming complexity of the problem. So in a previous work by Conrad and Rosen, they studied the problem in the communication complexity setting, and they show that they give an upper bound, which showed that there is a one-way communication protocol for this problem, which achieves an O of n to the 1/3 approximation using only O of n bits of communication. And on their lower bound side, they show that any protocol with n to the 1/1 plus c approximation ratio requires at least cn bits of communication. However, as you may know, or as you might see, this bound does not imply anything in the streaming setting, where you are allowed to have O of n log n bits. So because if we take c to be log n, then it doesn't give us any non-trivial lower bound. So in our work, we are able to improve the streaming communication complexity of this problem by showing that any communication protocol, which gives an n to the 1/4 minus O of epsilon approximation ratio, requires at least n to the 1 plus omega epsilon squared bits of communication. And this immediately implies that there is no one-pass streaming algorithm using O tilde of n space that can give a better than n to the 1/4 minus little o1 approximation. Okay, does anyone have any questions so far about the main results? Okay, so if not, I will start to introduce the overall techniques that we use. Okay, so one way to build a good streaming, communication protocol for this problem is to construct something called a load balancing sparsifier. This concept was first introduced by Conrad and Rosen, and essentially it is just a subgraph which is able to preserve the optimum load of any subset of clients. So what do I mean? Well, if I'm giving a subset of if I'm giving a subset C of clients, I'm going to let max load of C denote the max load on the graph just restricted to C on the left side and R on the right side. Okay. And so, yeah, so you can think of this as like the max load of just a subset of the clients. Okay, so then we say that a subgraph H of G is an alpha load balancing sparsifier if the max load of any subset of in H is at most alpha times the max load in G. So for example, in this graph, if I take C to be these 3 clients over here, and we see that the max load over here is 1, right? Because we have this matching that we can use to get a load balancing assignment of we can use this matching over here to get a load balancing assignment with only max load 1. And in this sparsifier graph, because these matching edges are preserved, I still have a max load of 1 with this C. Similarly, in here, if I take C to be this set of 3 clients, then the max load is 2, right? Because any assignment of these guys requires these two edges to map to the same vertex on the right side, which means that, and as you can see in this sparsifier graph, I also have the max load being 2 because these edges are preserved. Okay, yes?
Think about less than 1.
More than 1. So alpha is an approximation factor. So the max load of the subgraph might be bigger, right? Because it's possible that there is some maybe big matching that is not preserved, which means that maybe before with the matching, the max load is 1, but without the matching, the max load is like 100 or something. Yeah, so alpha. Yeah, so alpha alpha could be much larger than 1, yes. Yeah. Now, actually the previous example that I talked about with the matching, it turns out to be actually an equivalent characterization of this problem. So one equivalent definition of a load balancing sparsifier is that I find a subgraph H such that for any subset of vertices on the left side, the size of the maximum matching going from this side to the entire right-hand side is approximately preserved, up to a factor of 1 over alpha. Yeah. So in other words, if any subset of clients has a big matching leaving this subset, then there should still be a 1 over alpha factor big matching in the sparsified subgraph. Yeah. Okay, so right. So given this definition of load balancing sparsifiers, we immediately see that the load balancing sparsifier gives you a one-way communication protocol. In particular, if alpha receives any subgraph, she can just compute a load balancing sparsifier of this graph and send it to Bob. And the sparsity, the number of edges in this graph, will be the communication complexity of this protocol. And Conrad and Rosen showed that any bipartite graph contains an n to the 1/3 load balancing sparsifier with 2n edges. This would imply that you can always get a communication complexity. Sorry, you can always get a communication protocol with approximation factor n to the 1/3. Okay. Now, what we show in our paper actually is that this load balancing sparsifier actually characterizes the problem of the characterizes the communication complexity of this problem. Namely, we show that an alpha approximate protocol with an alpha approximate protocol for the load balancing problem of communication complexity T of n exists if and only if for all bipartites graph G, there exists an alpha load balancing sparsifier of size O tilde T of n. So in other words, the communication complexity of this problem is large if and only if there exists some graph that cannot be sparsified. And the way that we sort of show this equivalence is through a new combinatorial object we define and construct called the matching contractors. Okay, so and essentially the idea is that these graphs are exactly characterizes the set of all graphs that cannot be sparsified. So in order to define a matching contractor, I will first define a vertex expansion. So given a graph G and a subset of vertices, we will say that the vertex expansion of this set is the number of neighbors of this set outside of S divided by the size of S itself. Okay, so for example, in this set, this S over here has 2 neighbors outside, so we say that the vertex expansion is 1/2. And the definition of matching contractors is as follows. So suppose that we're given a graph, a bipartite graph like this, and I'm going to, so a matching contractor is a graph whose edges is made of a union of what we call contracting matchings. But what is a contracting matching? It is basically as follows. So if I have a particular matching like this, M, I will let LM denote the set of vertices on the L side of the matching. And then I say that this matching is alpha contracting if after removing the matching edges, LM have small vertex expansion. So in this case, with the matching over here, this LM, of course, has vertex expansion 1 because it's on one side of the matching. But after we remove this matching, the vertex expansion becomes 1/2 because all the other edges coming out of LM is captured by these 2 vertices over here. And so this is a contracting matching. And then the graph is a matching contractor if every single edge is, if the entire set of edges is comprises of a union of contracting matchings. Okay. Does anyone have any questions about this definition? Yeah. Okay. Yes.
It could actually be spanning the entire graph or some subset.
Just a subset. Yeah. This matching does not have to be spanning the entire graph. It's just for any particular matching. If I look at the vertices on the left, on the L side of the matching, and then all the edges coming out of this vertex of these vertices that are not matching edges have to be captured by a small set of vertices on the right side.
So for every edge, there exists some set of vertices for which that set of vertices is matched to the other side, and that edge is contained in that matching.
Yeah, so for every edge, yeah, there exists a contracting matching where the edge is part of where this edge is one of the matching edges. Yeah. So these bolded ones. So for example, with these other edges over here, there will be some other matchings where these are the actual matching edges. Yeah. Okay.
And how small? Like you're saying that if I delete the matching, the number of neighbors will reduce by some time.
Yes. So 1 over alpha. So an alpha matching contractor means that all the non-matching edges is captured by 1 over alpha fraction of vertices on the right-hand side. Yeah. Okay. So yes. Right. So essentially, sorry. Yes. Okay. So our first main result is that we prove a chain of equivalences between between communication complexity, the complexity of load balancing sparsification, and the existence of dense matching contractors. So specifically, we say that there exists bipartite graphs which do not contain an alpha load balancing sparsifier of size T of n, if and only if there exists a 2 alpha matching contractor of size O tilde of T of n. In other words, so this first theorem basically says that up to some log n factor, that a graph cannot be sparsified under this load balancing sparsifier definition, if and only if there exists dense matching contractors.
It's the same graph.
Yeah, so essentially, if it cannot be sparsified, it has to be a matching contractor. These are the only one, because so it's not too hard, so as I'll show later, it's not too hard to see that you cannot sparsify matching contractors, and also dense matching, and also there exists some graph that cannot be sparsified if and only if there exists dense matching contractors. That means basically these are the only graphs that cannot be sparsified, essentially. Yeah. Okay, so and then we also show that there exists an alpha matching contractor of size omega n, if and only if the one-way communication complexity of if and only if the one-way communication complexity of O of alpha approximate load balancing is at least omega tilde T of n. In other words, there exists dense matching contractors if and only if the communication complexity of this problem is large. So to give you an overview of this chain of equivalences, we start off by trying to get streaming lower bounds for this load balancing problem. And we want to use communication complexity to get the streaming lower bound. And to prove the communication complexity, we first show that communication complexity lower bounds implies the non-existence of load balancing sparsifiers, right? Because existence implies a low complexity. So high complexity implies the non-existence of low balancing sparsifiers. This implies the existence of dense matching contractors, which is that I can pack many contracting matchings into the same graph. And this in turn can be used to construct hard instances to the communication complexity problem. Hard instances to the load balancing problem in the communication setting. So these equivalences, so this means that all these three things are equivalent. And we show the existence of n to the 1/4 minus little o of 1 matching contractors. So the alpha is n to the 1/4 minus little o of 1. And the size is 1 plus omega 1, little omega 1. So the size, their size is bigger than polylogging. And this implies immediately that the one-way communication protocol has complexity at least n to the 1/4, and also it implies a non-existence of n to the 1/4 load balancing sparsifiers. And finally, this also gives us our lower bound for streaming via the reduction. Yeah. No, little omega means it's like
Into the little omega one.
yes, sorry, that, yeah, sure, it should be big omega, my bad, yeah.
Big omega there.
Wait,
What does that mean? N to the 1/4 minus. No, sorry, which one is it?
The little omega.
Oh,
yeah, sorry, yeah. Okay, oh, no, okay. Yeah.
In this picture, so you said the thing you prove is what's on the bottom left corner.
Yes.
So is the right hand side necessary for
This one?
this whole cycle? Yeah.
Yeah. Well, I guess technically it is not required to get these two things, but I'll explain later why this is kind of interesting, because this entire setup is very similar to the matching sparsifier and Rusa similarity graph. Yeah, I'll explain actually right now, actually. Yeah. So basically, the general flow of our work is very similar to that of Goel, Kapralov, and Kana, which uses matching sparsifiers and Rusa similarity graphs to characterize the communication complexity of maximum matching in the streaming setting, and in the streaming and communication complexity setting. And the idea is that they define something called a matching sparsifier, which is just a subgraph which preserves the size of which is a subgraph which preserves the set of maximum matching between any two sets of vertices. And they show that the non-existence of these matching sparsifiers is equivalent to the existence of so-called dense Rusa similarity graphs, which I'll show you the definition in a bit, but these are very important objects in extremal combinatorics and streaming, and has applications in all sorts of different things. So these are very important class of graphs. And then they show that that by constructing like dense Rusa similarity graphs, they can give lower bounds on the one-way communication complexity for the maximum matching problem. So our results is essentially analogous to their results in the load balancing setting. So they define the matching sparsifier to be a subgraph such that for all S and T, subset of vertices S and T, the size of the maximum matching between S and T is approximately preserved up to some additive factor, up to some additive error. And then the load balancing sparsifier says that for any subset S, we want to approximate just the size of the maximum matching leaving S. Right. So this notion of a sparsifier is weaker than the matching sparsifier. And conversely, the matching contractor, which is the dual notion of matching sparsifiers, can be viewed as a stronger version of this Rusa similarity graph. So the Rusa similarity graph is a dense graph where every single edge is part of an induced matching. So induced matching just means I have two sets of vertices and a matching between them, such that all the other edges adjacent to these vertices are leaving this two sets, like this. And a contracting matching basically says that, okay, I have a matching, and I'm only looking at one side of the matching, but I need all the other edges leaving to be contained in a tiny set of vertices. So this matching contractor can be viewed as a stronger notion of a Rusa similarity graph. And actually, we show that the construction that we use for matching contractors can also be used to construct Rusa similarity graphs up to polylog density. Yeah. So, right. So Yeah, so that's sort of to answer Eric's previous questions. Yeah, so that's sort of the reason why we look at this sparsifier problem is because it is closely related to this matching sparsifier problem. And just like the matching sparsifier problem, which is shown to be equivalent to the existence of dense residuosimilarity graphs, we show that the load balancing sparsifier problem is equivalent to the existence of these dense matching contractor graphs. Yeah. This
He said that matching contract is a dual of,
load balancing sparsifiers.
is that dual in some sense, like it's actually some sort of duality? or-
Yes, I will also get to that very soon. Yeah. Yeah, so right. So yeah, but yeah, it is technically true that in order to get the complexity bounds, we don't need to go through the matching sparsifiers. Yeah. Okay. So yes. Yes.
It's only for this specific way of constructing that.
Yeah, so the construction gives residuosimilarity graphs of the same density, but of course the density for these matching contractors is much less than the optimum densities that we can get for residuosimilarity graphs. So it's not like an optimal construction or anything.
No, I'm not asking the optimal or
Yeah.
anything. I'm just asking, is there a way to go from any matching contractor to a residuosimilarity graph, which has lower density? Is that what the sentence means? Or you're just saying that this particular way also gives you a residuosimilarty graphs?
Yeah, like you should be able to go from matching contractors to residuosimilarity graphs up to some.
Up to some factors,
Yeah,
yes. Okay,
yeah.
all right, okay.
I think like I think it might be easier to look at it actually the primal version of the problem, because the primal version of the problem, I think it's easy to see why one problem is strictly easier than the other one, and because of these equivalences, right? So in the primal problem, we see that the matching sparsifier problem, you need to say that for all S and T, you preserve the size of the maximum matching between S and T. Whereas for the load balancing sparsifier problem, essentially you just for all S, you want to just preserve the size of the maximum matching leaving S. So this should be easier than the other one. So, and because these are equivalent to the corresponding sort of dual problems, then the dual version of this has to be the dual version of load balancing sparsification should be harder than the dual version of matching sparsification. Yeah. Okay, so with all these things aside, we can go into some of the details of our proofs and constructions. Okay, so right, so to prove the equivalence between matching contractors and load balancing sparsifiers, we essentially use a linear programming duality argument. So, well, one direction is actually easy because again, it is easy to see why a matching contractor cannot be sparsified. But on the other hand, in order to prove the other direction, we first write the load balancing sparsification problem as a linear program in which we use a linear program to try to find the sparsest subgraph of a particular graph that preserves the size that preserves the size of the maximum matching, leaving any subset of vertices. And by taking the dual of this LP, we can actually use the dual solution, the optimum dual solution, to sample a dense matching contractor. So if the primal objective value is large, in other words, if we cannot find a very sparse subgraph that preserves all the load balancing solutions, then that means that we can use a dual to sample a large matching contractor. Right. So this is why this is sort of a dual object that I alluded to earlier. Okay, so now, and then to show that alpha matching contractors imply communication complexity, essentially we just need to use matching contractors to construct hard instances to the load balancing problem in the communication complexity setting. And the idea, again, is very simple. Suppose that the graph that Alice obtains is a matching contractor. So I want to say that this means that Alice has to send a lot of information to Bob. In particular, for every single matching in this graph, Alice has to send a large fraction of these matching edges in order to preserve the approximation factor, right? Because if you, for example, if you see in this contracting matching, right, if Alice fails to send these 4 edges to Bob, then all the other edges in these 4 vertices are matched to these two vertices over here, right? So if Alice does not send these, these four matching edges, then Bob is forced to output a solution that matches these vertices to these two guys, which will give you a bad load balancing solution. So this means that every single matching else basically has to send a constant fraction of these edges. And this means that she has to send the number of edges she sends has to be on the order of the density of the input graph. Okay. Okay. So this is sort of a rough sketch of why these can be used to lower bound the communication complexity of the problem. So with all these equivalences established, the only thing to left to do is to actually construct these dense matching contractors. So to give you an idea of how we construct them, the idea is to, okay, so I'll state the result first. So we show that for L equals N and R, and the size of R equals root N, and any sufficiently small epsilon, there exists an alpha matching contractor with alpha equals n to the 1/4 minus epsilon, and each matching has size root N. Okay. And sorry, and the total number of edges is N to the 1 plus omega epsilon squared. So the idea is actually very, very simple. So we're going to let L be the set of binary strings of length 2k, and we're going to let R be the set of binary strings of length k. Okay, so here we see that if L, so here we see that the size of R is root N. Okay, and the idea to construct each matching is to just pick a subset of indices, a subset of k indices. And for these k indices, I'm going to, well, let's say S1 is the set of indices that I picked. I'm going to fix the bit string outside of these indices, as you can, which you can see in the red. And I'm going to vary over all possible combinations of the bit string inside these indices. And I'm going to use the varying indices to construct a matching of size 2 to the k, which is root N. And this is going to match to R just by matching the corresponding indices to the same string on the right side, right? So this gives me one matching of size root N. And of course, I can construct root N of these matchings all disjoint to get N edges, right? Okay, but now what if I picked another set S2 and constructed another root N matchings of size root N the same way? Well, the claim here is that S1 and the S2 are contracting with respect to each other, as long as the intersection between S1 and S2 is small. So why is this? Well, if we just look at this picture, if you look at S2, S2 has a small intersection with S1, which means that the complement of S2 must have large intersection with the complement of S1. But remember, for each matching, the complement part of the matching has to be fixed. Sorry, yeah. For each matching constructed from S1, the indices in the complement of these indices have to be fixed to be a constant. But on the other hand, S2 is actually used the indices in S2 on the other hand are actually used to map to the other side. So this means that if you look at this picture, the indices, these three indices over here, which have values 0, 1, 0 in S1, are all fixed inside of S2, which means they can only map to these two vertices that end with 0, 1, 0 over here. This is basically the only main idea of this construction, right? It is quite simple. It's just that saying that if S1 and S2 have small intersection, then their complements must have large intersection, which means that if you look at the set of indices in S2, and you intersect it with this matching constructed using S1, all of these indices must be fixed. Yeah. And because these indices in S2 must be fixed, they must be matched to a small subset of vertices on the right-hand side. And then finally, in order to actually construct a dense matching contractor, we just need to find many indices, many subset of indices that have small pairwise intersection, which is done through standard arguments in using the probabilistic method. And this and it turns out that as long by balancing the expansion, which is given to you by the intersection size, and the density, which is the number of these subsets of indices you can find, you can get the result in the main theorem. Yeah.
A set S1.
Yeah.
Say these indices could be fixed, then you construct like this square that says matching. Fixing, you also go over all fixings, or do you just pick one which is?
Yeah, so each matching corresponds to one possible fix of the complement indices.
I see. Just one
Yeah.
square then.
Yes, exactly. Yeah. For each S1, the square root of n matchings. Yeah. Right. And again, each matching has these fixed indices and these variable indices. And because if I pick another set S2, which have small intersection with S1, the variable part of S2 will have a large intersection with the fixed part of S1. Yeah. And because of that, the set of possible things that S2 can map to is only a small set on the right side. Yeah. Okay. Yeah, so that is all of our all the things I want to talk about. And then for some open problems, the obvious ones is that can we close the gap? So in the one-way communication complexity setting, the optimum communication protocol has a complexity has approximation factor into the 1/3, whereas our lower bound gives it into the 1/4 minus the little o1. Yeah. So can we get improved one-way communication protocols for this problem, which would come through like a matching sparsifier, or which could come through a load balancing sparsifier. And also, we might ask, can we close the into the 1/2 and into the 1/4 gap in the one-path streaming algorithm? Can we find a better than into the 1/2 one-path streaming algorithm for this problem? And another question is, can we find better upper or lower bounds for a multipath streaming algorithm? And again, Russo similarity graphs, as I mentioned before, are very useful. So since matching contractors are kind of analogous to them, another open question is, can we find other applications of these matching contractor graphs? Yeah, and that's all I have to present today. I guess it's a shorter talk. Yeah. So yeah, does anyone have any questions?